I'm Don Barry. I chair the Physical Sciences Department here at Mesa, and I coordinate the STEM lecture series. So thanks for showing up. We've already had our first talk, actually, so we have 9 additional talks this semester, and I have a nice flyer if you need one. And this is not required, but if you want to sign the sign-in sheet, I'll pass this around just in case your professor contacts me the next morning and says, "Hey, was Joe here last night?" And I can say, "Yeah, Joe is here." So that's kind of optional, but I'll send it around. And before I introduce the speaker, just some housekeeping items. So we are filming tonight, and eventually we'll post tonight's talk online where you can watch it at your leisure. So we would ask that maybe try to avoid the center aisles, if you need to get up. Also, it's easy to leave. If you need to leave in the middle of the talk, kind of sneak out, and you can walk down the stairs in the back. There's the stairs there, and you can kind of sneak out the back. Just be careful that the door has a tendency to slam, and it sometimes is picked up on the video, so maybe just try to close the door a little bit quietly. And I should point out here we have an honored guest tonight, Dr. Isabel O'Connor, our new Vice President of Instruction. So thank you, Dr. O'Connor, for being here. And thanks to all of you as well. So I'll send the sign-in sheet around, again optional. But if you'd like to sign it, go for it. Does anyone need a flyer? Our events? Okay. You need one? Okay. Who else? All right, there you go. Excellent. Good. Hey, how's it going? Good to see you. Go ahead. There you go. Grab a flyer. Okay, well, I'm pleased to introduce tonight's speaker, Dr. Joey Fedro. Joey is an astronomer. He got his PhD from Kyoto University, creating computer models with mathematical equations about as long as that entire screen. And during his last talk, he put up these obnoxious equations. Everybody kind of gasped. But then he said, we don't solve these by hand. We let the computer solve the equations.
That's right.
So if you're good at coding, you can do what Dr. Fedro does.
Yeah.
So without any further ado, Dr. Joey Fedro.
Thank you. Thank you very much. And I should also add to that note, even if you're not very good at coding, you can still do a lot of this modeling that Don was mentioning, because a lot of that software is really available. It's open source. We can talk more about it later. So anyway, without further ado, let's begin. So thank you, Don, for the introduction. And it's great to be back at Mesa College. All right. So as you can see, the title of my talk today is Kintsugi, the art of broken symmetry across space and time. Now this might sound kind of like a bit of a crazy idea, and perhaps it is. But as I was sort of alluding to earlier, there are 3 main topics that we're going to be covering tonight. The first is this idea of Kintsugi, which as we'll see is kind of a sort of Japanese philosophy and art, part of the wabi-sabi sort of family of things. The other main idea is inflation of the early universe. This is what I mean by the origin of the universe, and our theories of the origin of the universe, and also dark energy. All right, essentially our collection of theories and ideas of what is the fate of the universe, the expansion of the universe, and all that stuff. So those are the 3 main topics we're going to be covering tonight, with Kintsugi being the essentially connecting agent between inflation and dark energy. So that's the talk in a nutshell. Let's begin. So I would like to start this talk with a musical interlude, if I can find my music. So the question is, I'm going to play, oh my god, I'm actually ruining it, because that's, oops, hopefully nobody saw that. So I'm going to play a little ditty here. Sorry, we were testing before. Listen carefully. Sounds beautiful. Everyone can hear that? Yeah? I think that's enough. So the question becomes, what was that sound you just heard? Can anyone venture a guess? Oh, you're looking at it. All right, fair enough. Yeah, it was kind of ruined there. Sorry, I was trying this new, this should have been not so big. So yes, unfortunately the surprise was ruined. That sound was the sound of the Big Bang. Okay? So that actually was, like I'm not kidding around, that was literally our best impression of what the beginning of the universe sounded like, all right, according to the data, with the data being this picture right here, which is essentially a map of the temperature differences, all right, of the universe when it was only about 380,000 years old. Okay? So this map is called the essentially cosmic microwave background, and we'll talk a little bit more about this map in due time in today's talk. But without further ado, let's listen to another sound, all right, which is, you hopefully didn't just ruin it, but so the question is, what is this sound? Sorry, it shouldn't be that loud. Answer is?
Vase breaking.
Yes. Pretty good. A vase breaking, or I think I said a dish breaking. Okay? Close enough though. And as we'll see, or as you can see even right here already, Kintsugi is this Japanese technique of fixing broken pottery. So the general idea behind Kintsugi is that you have something that was cherished, something that was beautiful, it was then broken, but then the act of repair could actually make it more beautiful. So that's the general idea. So it's not a sad thing that this broke, this treasured dish broke. It's actually a beautiful thing because the new creation is perhaps even more beautiful than the previous. So we're going to be talking a little bit about that, again, as our kind of common theme. So the question that we want to begin with is, how are those two different sounds related? A broken dish and the beginning of the universe. All right? Well, in order to talk about that, we got to talk about Kintsugi a little bit more. Okay? So, quick one-slide introduction to Kintsugi. What is it? Well, it is essentially a 500-year-old Japanese traditional art. All right, started by Shogun Ashikaga Yoshimasa. And as I was talking to before, it's about beauty from broken symmetry, embracing the impermanence of matter, and it related to the Japanese philosophy of wabi-sabi. And actually, oddly enough, this shogun, Yoshimasa-san, was actually from Kyoto, all right, from the Silver Pavilion, which is actually like down the road from my old office. So I didn't even know that when I created this talk, and lo and behold, the guy who did this 500 years ago was just like down the street. So it's a small world. So here are some examples of Kintsugi, all right? And if you're curious, why the name Kintsugi? Well, kin in Japanese means gold, okay? And so here they're using gold solder, all right, to connect the broken pieces. And I'm not exactly a Kintsugi expert, apologies. There are, quick superficial overview of those. There are various techniques of Kintsugi. For example, in this technique, you pretty much have all the broken pieces, so you can connect them all relatively seamlessly. In other cases of Kintsugi, though, which I didn't actually prepare an example of, but if you can imagine that this piece was missing, then they may actually take another dish, possibly break it on purpose, or maybe they just have a collection of broken pieces that match that shape, where they can, sand it down a little bit, and then they'll fix the dish with another piece, okay? And that also is considered a beautiful thing, okay? Or in other examples, as you can see in this particular case, if they're missing it, they might just fill it completely with gold if it's small enough. So those are kind of three main techniques of Kintsugi. Here's just one more example showing, Kintsugi. So the goal of this talk is to bridge and essentially move from Kintsugi locally, 500 years ago in Japan, out globally to space-time. Okay. And my main thesis here is this. Kintsugi would not exist without the breaking of symmetry. And by symmetry I mean the dish that you had originally, the cup, the plate, the bowl, whatever you want to call it. Presumably it had some kind of beautiful, symmetry to begin with. It was then broken, leading to the necessity of Kintsugi. Also, I would argue that both the origin and fate of the universe might also depend upon broken symmetry. Okay? So let's find out what I mean by that, how we can actually model both the origin and fate of the universe using broken symmetry. What does that even mean, all right, from like a modeling perspective? And I will take it from there. Okay? So, let's start with the beginning of the universe, all right, inflation. So inflation is sometimes considered the ultimate free lunch of the universe, because from the empty vacuum of space, you got everything that you have today. This room, all right, me and you, your computers, your cell phones, this pizza, okay? So The idea behind inflation, so I think maybe Big Bang is more common than inflation. Sometimes, people talk about inflation, Big Bang, inflation happened after the Big Bang. Technically speaking, the hot Big Bang is a result of inflation. And I think this chart just does a really nice picture showing this, where you have essentially the beginning of what we consider our universe, essentially quantum fluctuations giving rise to this period of rapid acceleration known as inflation. About 380,000 years after that event, you had what's called the recombination, or this picture from before, the cosmic microwave background. And if you look closely, you can kind of see this map here, which is the same map of the temporary anisotropies from before. And then, essentially, as the universe got older and older and cooler, it was getting bigger and bigger and bigger. All right. The general idea was that eventually this expansion would slow down, gravity would begin to dominate, and then the universe would collapse back onto itself. But alas, when astronomers actually went out and looked to see this effect, they saw the exact opposite. Okay? And this was back in the late 1990s with the high supernova teams over at Berkeley, one at Harvard. And essentially, they were so shocked by their findings, they actually sat on the results for about 6 months to a year because they figured this must be wrong. So they double-checked everything. Then eventually they're like, all right, man, this is it. Like, it is what it is. And sure enough, their results were corroborated by the other team. So, point is, that's a different topic for another day. But the point is, eventually, this expansion actually reversed. Rather than getting slower and slower and slower, it actually got faster and faster and faster. And that was very recent, essentially today from a cosmic perspective. And this is what we call this dark energy accelerated expansion. So perhaps you've heard the term dark energy. This is what we mean by dark energy. This mysterious, rapid, accelerated expansion of the universe. And we'll talk a little bit more about that when we get to it. And these two satellites here, WMAP and Planck, these were two satellites that we actually sent out into space to study the cosmic microwave background radiation. WMAP went out kind of early 2000s. Planck went out around 2013. Planck is our most recent, essentially the highest resolution map of that cosmic microwave background that we not only have now, but that we'll ever have. Like literally that map I showed you cannot get any more detailed. We're not limited by our ability, we're actually limited by the physics of the universe. So that is a really greatly detailed map and it's wonderful. Point is, this is our universe in a nutshell from an evolutionary point of view. Started with quantum fluctuations leading to inflation, eventually. Today, we live in a dark energy accelerated expansion dominated universe, and we don't know what's going to happen in the future. Okay, but we'll get more into this in a moment. So this general big picture of the universe is what's known as cosmology, right? And theoretical cosmology is the idea of essentially studying, the foundations of the universe as a whole. Okay. Now, I mentioned this idea of inflation. The universe started with this sort of Big Bang. Okay. But there were three cosmological problems that come about as a result of basic theories of inflation. These three ideas are known as the horizon problem, which is another way to say it is, why is that CMB map so uniform? Because think about it. I didn't really talk about it in detail, but this is a map of the whole universe. Whole universe. And what this map is essentially saying is that everywhere you look in the universe, it's about the same direction. But then that becomes a bit of a problem because it's like, well, wait a minute. Like, if the universe, as big as it is, if you have like two ends of the universe, and if they're not in contact with each other, how could they come to thermal equilibrium? How can they be at the same temperature? How would they know to be even at that temperature, right? So this is a bit of a problem. And inflation actually solved one of these problems with a particular model. Anyway, another problem was this flatness problem. Why does the universe appear to be so flat? Inflation also solves this problem, if done correctly. And the way it solves it is by saying that the universe appears flat only because inflation essentially expanded the scale factor exponentially, which is just a complicated way of saying that it's just so big now that it appears flat. Just like when you're out on Earth's surface, it appears flat, assuming it's more or less a flat field. When in reality, the surface is actually curved, all right? And this is because, if you can kind of think about it, during inflation, the universe went from a microscopic size, think of it like an electron, to something macroscopic, like a golf ball. So think about that. Going from an electron to a golf ball, like in like a fraction of a second, in a fraction of a second. Okay? So if you were on that electron to begin with, and suddenly became as big as a golf ball, all right, from your perspective, it's huge. So therefore, the geometry appears flat. So that's how kind of inflation solves this idea of a flatness problem. There's also this idea of a magnetic monopole problem, but we don't need to really worry about these things. Point is, inflation, if done correctly, solves 3 big cosmological problems that were present. Okay? And if you're curious, because I didn't really give you an answer, inflation solves this magnetic monopole problem. The problem is that if you have an inflationary theory that breaks symmetry in particle physics, you get what's called essentially a monopole. And so if I have an inflation, you're breaking symmetry, there should be a whole bunch of these magnetic monopoles, but none have ever been observed. If you were to observe a magnetic monopole, like you mentioned up in it, you would know it probably automatically, because it's never been observed. And the way inflation solves this problem is by dilution. Inflation says, well, yes, I broke symmetry, and yes, these monopoles were generated. But because the scale factor essentially expanded exponentially, they were all diluted out of your field of view. They were all kind of pushed out from your causal, bubble of the universe. So that's how inflation solves that problem. Point is, don't get too stuck in the details. Try to just stick with, the general idea, which is, just, kind of absorb the general qualities and kind of hopefully just get an idea of how this will relate to dark energy in a moment. All right. So with that said, I'm going to just really very briefly walk through the origins of how we modeled inflation from its beginnings to essentially the modern day interpretation. And I'll try to do this in a pretty not too technical level. So real quick, this plot here you see is a plot of the potential energy, all right, via phi, and phi, which is a scalar field. Okay. Point is, just think of this as like a bowl and a marble. Okay? And if you have a marble in a bowl, if it's at the bottom of the bowl, it would be essentially stationary, right? But if the marble were to deviate anywhere away from that minimum, it would roll back down to the minimum. Sounds about familiar, right? So one way to model inflation in particle physics is with a potential of a particular shape. Okay? In this case, you have this particular kind of shape, where you have a V, all right, of 0 is 0, and this is what's considered the true vacuum energy. So if you have a particle at the bottom of this well here, it's going to be stationary, and this is what's considered the true vacuum state. Whereas if you have the same potential well, but higher up, all right, if a particle found itself here, from its local perspective, it thinks it's fixed. It thinks it's at the lowest energy, right? But really, it's not. And that's why this is called a false vacuum as opposed to a true vacuum. And then this idea of quantum tunneling is that, well, if it's a particle, all right, then it's subject to the laws of quantum mechanics. And therefore, it has the ability to tunnel through potential barrier, potential wall. So eventually, it's going to tunnel, maybe not today, maybe it's tomorrow, but if you're very patient, and the universe is very patient, eventually, this particle, which we call the inflaton, will tunnel from the false vacuum to the true vacuum. And this quantum tunneling transition to the true vacuum gives rise to inflation. But I'm sorry, I shouldn't have actually gone ahead real right there. But the problem here is once this model has inflation starting, it never finishes. So Alan Guth put this model forward first back in 1981, and it was great because he was able to easily generate inflation with this very simple model. But like I mentioned, that problem was once it started, it never finished. And this is what's called the graceful exit problem. Okay? So about a year or two later, Andy Albrecht and Andy Steinhardt, along with Andre Linde over in Russia, simultaneously, proposed a new idea called new inflation, which said, hey, well, what if you just take different shape potentials, such as this, all right? And if once again you had the inflaton in a false vacuum state, all right, then by rolling down to the true vacuum, this rolling, this motion of the inflaton would also give rise to inflation. But in this model, that inflation eventually ended. So first, everyone rejoiced. This is great. This is beautiful. Wonderful. Just what we wanted. But Then came the interpretation. Wait a minute. From a physical point of view, this is kind of unlikely, because why would the inflaton find itself right at that particular spot? It's an unstable equilibrium, right? Anywhere away from this equilibrium point, you're going to fall down. So it would be very unusual for the inflaton to just happen to find itself at this particular point, right? So this was kind of like what's called the fine-tuning problem. Yeah, where it's like, yeah, you know, you kind of solved the graceful elliptic problem, but it's not really very physically likely to be in that position to begin with. So new inflation was an improvement, but still had some problems. About a year or two later, once again, Andre Linde stormed forward with his idea of chaotic inflation, which is beautiful because it sounds, you know, chaotic and crazy, but it's actually the simplest model of inflation. So here we go. In Andre Linde's model, he said, hey, wait a minute, you guys are all nuts. Just start with a very simple parabola, just like this. No different from parabola you've seen back in elementary. And in this particular case, the inflaton would initially be at equilibrium. It would be at a true vacuum state. But if you had quantum fluctuations, all right, which could then essentially perturb that inflaton away from the equilibrium state. So for example, boom, suddenly you find yourself being, you know, perturbed up here. As the inflaton then rolls back down to the true vacuum, that rolling motion once again would give rise to inflation. Okay? And this was much more natural. The potential is a very natural potential. And by natural, I mean in physics, this is agreeable, meaning it makes sense from a theoretical point of view, from a modeling perspective. We'll leave it at that. But you can see qualitatively, I mean, this is the simplest shape I've shown you so far of the three. And furthermore, the inflaton starts at 0, at the true vacuum, which is what you would kind of naturally expect. And quantum fluctuations are everywhere in the universe. So all things considered, this model made a lot more sense, and it solved all three cosmological problems, just like the initial inflation did, but it also had a graceful exit. So this was great. And when people talk about inflation today, for those of you taking Astronomy 101 or and beyond, when you read about inflation, you're kind of really reading about chaotic inflation from Andre Linde. Okay, so here's just a little more perspective about it. This potential here, this parabolic potential, can be modeled as a 1/2 m squared phi squared potential. You can think of m as the mass, or this whole thing as the curvature. Phi, once again, is that scalar field. But don't worry about it. Again, don't worry about the details here. The main thing is that any potential could work as long as it has a region somewhere that is flat enough for the inflaton to slowly roll. It's kind of the key there. And you got to kind of look at the differential equation to see why that is. So we're not going to worry about it tonight. Main thing is these quantum fluctuations perturb the inflatons. The inflaton slowly rolling down gives rise to inflation. That inflation gives rise to the universe expanding exponentially, which eventually results in a hot Big Bang that we then read about in books. Okay. So, main point I want to drive home here is that even something as simple as a parabola can determine the fate of the universe. Okay. That's really the take-home message from all these slides so far. And this equation here, this is just essentially what we call a differential equation, which is a way to model the behavior and evolution of the scalar field phi. Okay? And you can see here, this V is for the potential there. And that's how the shape of the potential dictates the evolution of the scalar field. So, now here's some beautiful equations, just like Don was talking about from before. But just like, back to never, don't worry about this. Don't worry about the details. The main point of these slides that I'm about to show you is the fact that everything I've been talking about so far is calculable. It's predictable. We have theories that make predictions. And those predictions look something like this. And those potentials that I was showing you show up right here. Okay? So this scalar power spectrum, don't worry about what that power spectrum is. Don't worry about it. The point is, it has an equation, okay, that leads to observables. And those observables depend on A of S, which depends upon the potential. All right? Or it depends upon other things, which depend upon these parameters, which again fundamentally depend upon the potential, the derivative of the potential, and the second derivative of the potential. Potential is very important. Hopefully you can see that. So again, don't worry about those equations. Point is, everything I've been talking about makes predictions. And we are now at our point in human evolution where we can actually make those observations for the first time in our history. So, these parameters here are called the slow roll parameters because again, remember I was talking about you need a slow roll to get inflation, but let's not worry about it. And there's another key thing I just want to highlight, the name, tensor to scalar ratio. Again, don't worry about the details. The main thing is this is an observable that is predicted by our cosmological theories. And at the end of the day, if you massage it enough, it boils down to just a very simple number, 8 over n, where n is the number of e-folds, which is to say the number of periods of inflation that we get in the early universe. It's about 60, between 50 and 60 more or less. So this very fancy tensor scalar ratio sounding thing from all these fancy formulas really just boils down to 8 over 60, okay, more or less. And just to kind of give you an idea of what these observations look like, all right, here are the Planck 2013 results. So remember, I showed you a satellite before, the Planck satellite, which took that cosmic microwave background radiation map, okay? And from that map, we can then extract, the data, play around with it, analyze it, and we can then plot the tensor to scalar ratio, that thing I just showed you, along with what's known as the primordial tilt on the x-axis. Again, don't worry about it. The main thing is we have that data, all right? We can then compare our models and their predictions to what the data actually shows, okay? And if you look here, this green kind of swath of color there is what we consider as the best fit model. And if we kind of zoom in a little bit, I also just want to highlight the history of the tensor to scalar ratio and the observations over the years. Back in 2005, all right, this is like the time before YouTube even. This was, we essentially constrained, meaning we said, all right, tensor to scalar ratio, we don't really know what you are, but we know you got to be less than 0.71, all right? And then just a couple years later, with that W map that I was talking about, that other satellite, we made an improvement. We said, you know what, actually it's less than 0.43. And as you can see, over the years, we've gotten it down lower and lower and lower and lower and lower to the point where it's now very, very well constrained to being less than 0.11. All right? And the main thing I just want to highlight here is that when you look at the data from Planck, our best data to date, the hilltop model of inflation is actually preferred. Where the hilltop is actually that model inflation that I called new inflation. All right, that I said wasn't very natural because of the fine-tuning problem. So this was a bit of a surprise to cosmologists because they were like, wait a minute, I thought Andre Linde's 1/2 m squared 5 squared chaos inflation was the best. And with Planck data initially, it was like, well, maybe we got to kind of rethink that. So this was a bit of a surprise. I mean, it's still not conclusive, and there's actually been some additional developments since then. Hilltop inflation, though, was a bit surprising that it still had some legs to it, okay? But this was a surprise, all right? And the main result that you could take home from that 2013 Planck paper is that perhaps broken symmetry models are preferred for inflation, okay? So that's where we are at, essentially, today with cosmology, inflation, and the Planck results. And again, the hilltop potential is an example of symmetry breaking in physics. So, now that we've started from the beginning of the universe and got into today with the Planck satellite, let's just take a moment to, take a deep breath, relax. Remember where we are. We're at Mesa College, San Diego. All right, this should look familiar. Now, if we were to go a little bit above where we are, we would see San Diego. All right, sure enough, from above. This should look also more or less familiar. But what if we were to go even higher? All right, we would see the polar, the curves of the Earth, kind of what I was talking about before. Appears black, but it's actually curved, right? Assuming you believe that. And you go further and further out, you start seeing more and more stuff. You see the Earth, you see the moon, you see the sun, all right? Go even further, you see the whole solar system, all right? You got our sun, you got all the planets going around it. It's all very beautiful. Go even further, you get the Milky Way, all right? And in case you weren't aware, our sun is just but one star in the Milky Way, somewhere in this neighborhood here, okay? But we're just kind of moving on out, going on a trip here. So if we were to go further and further out, if you consider this the Milky Way right there, you would see our surrounding neighbor galaxies, the local group, all right? If you go even further, you would see kind of what we call the Hubble Deep Field. All right, so quick show of hands. Who's familiar with the Hubble Deep Field? See people, very nice, very nice. So, just an example here. You look at this picture, and if I were to ask you, in this image, how many individual stars do you think you see? What would you say? Okay, we have 2. Reasonable guess. Any other guesses? 3? All right, maybe you've all seen this talk before. Essentially, yes. The answer is in this whole image, in this entire picture, all right, the only individual stars are 1, 2, 3, and there might be like 1 somewhere else. Okay? Point is, every other point of light you see in this image, every other point of light is a galaxy. So everything you see here, galaxy, 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 galaxy. Even these little pinpricks of light, galaxy, 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 galaxy. Everywhere. Okay? So it's like, all right, well, that's kind of interesting. That's a lot of galaxies. But, the image is probably huge, right? It's the universe. Probably, it's a massive thing, right? No. This image is actually, just to give you an example of the size, I went to the beach. I got some sand. I have a little grain here, okay? If I take this grain of sand and I hold it at arm's length against the sky, just like so, the amount of sky that this grain of sand covers is the size of this image. So everything you see here, every galaxy you see here, is contained within only a grain of sand held at arm's length against the sky. So then you can ask yourself, well, wait a minute, that sounds kind of crazy, because then you can start approximating, well, how many galaxies are in this image? How many stars are in a typical galaxy? How many planets are in a typical, galaxy? You start getting some basic numbers. Then you say, okay, well, about how many grains of sand would fill the entire sky in 360 directions? Probably a lot of grains of sand, I would presume. Then multiply that by whatever it is you're trying to calculate here, number of galaxies, number of planets, number of stars, whatever. You get some pretty big numbers, okay? So that's just one image. Boom. Hubble deep field. But we're not done yet, all right? Because if we were to keep going further and further out, then we would start seeing all these different galaxies blending together into this fine, large-scale structure, where all these veins of light are actually veins of galaxies, okay? And surrounded by voids. Notice this, shockingly, we have these massive voids all around the universe. And if we go further and further out, we just simply see more and more large-scale structure, all the way out. Okay. So that's our universe on the largest of scales, starting from Mesa College, going all the way out to large-scale structure. Okay. So now let's just do a little recap, a little inventory. All right. I essentially just showed you the whole universe. Okay. Right. You can think of that whole universe as being this pie chart. Everything you saw with your eyes, not even just in this talk, but everything you've ever seen with your eyes your whole life, and anything you ever will see for the rest of your lives, is actually only 4% of what's out there. So even when you look at that Hubble Deep Field image, with all those galaxies and just the one grain of sand, that's only 4% of what's really there. And you're never going to see the remaining 96%. And that's why we call it collectively dark matter and dark energy. So dark matter is the remaining 22%, give or take, all right, of matter distribution in the universe. We call this dark matter because we've detected it gravitationally, and it behaves like matter, but it doesn't. We don't see it, all right, like normal matter, all right. So therefore, we call it dark. Both because we don't see it, and B, because we don't know what it is, all right. Even today, we still don't know what dark matter is. Anybody know what dark matter is? No, because nobody knows. A lot of people have great ideas, but essentially it's still a mystery. Likewise, that's only 22% of the universe. Still the remaining 74%. That's all dark energy, all right? Which is essentially this idea of, and we'll talk more about this, what's driving the accelerated expansion of the universe, okay? Now, unlike matter, okay, this is energy. It just behaves like essentially like anti-gravity, okay? Where rather than causing two things to come together, it causes two things to repel, okay? And again, it's dark because, well, we don't see it, and ultimately we don't know what it is, okay? Now, to give you an idea here of this pie chart in our universe, this is like equivalent to if you had an entire pepperoni pizza, all right? But all you got was literally this one slice. That's like not even a whole pepperoni. So when every time you look at the universe, and even like, you go for a walk in the woods, you look at the sky, you go to Palomar Observatory, even if you see like the most deepest, beautiful, wonderful image, you're still only seeing 4% of what's really there. Okay. Don't forget that. All right. So here we go. Maybe some of you all looked east last night. Maybe you saw this view. All right. Oops. looking at the sky. So, and let's say, you're a patient observer, and let's say, you waited 3 times 10 to the 9 years, or 3 billion years. Well, your view is going to change a little bit, okay? Because the Andromeda Galaxy, one of our neighbors in the local group I showed you earlier, is actually on a collision course with the Milky Way galaxy. So our 2 galaxies are scheduled to collide in, I don't know, about a couple billion years. Now, this image is obviously not a realistic image, it's just kind of giving you a qualitative idea here. But interestingly enough, and I have a minute I can talk about this, not if, but when these 2 galaxies collide, our galaxy and the Andromeda Galaxy. Let's say I'm here, once again, a couple billion years from now, giving a talk, and 2 galaxies, boom, collision starts. What happens to this room? Holy moly, what do we do? What's going to happen? Beautiful, wow, why? Yes?
It's mostly just empty space.
Beautiful. Yes. Wonderful. Yeah. So if you look at a galaxy and you kind of just start taking averages, one way to look at it is that in a typical galaxy, the distribution of stars is essentially like having a marble in Texas and a marble in New York City. So then the question becomes, well, okay, so what's the probability of those 2 marbles colliding? Pretty low. And therefore, we expect when the 2 galaxies collide, granted, the constellations will change, our perspective will change of the night sky, but in terms of stellar collisions and explosions, should be more or less smooth. Also we can say, well, supermassive black holes at the center will collide as well eventually. But essentially, if I'm giving a talk, as far as I'm concerned, it should be pretty okay initially. Anyway, getting off base here. Point is, if you're a really patient observer, what would you see in 3 times 10 to the 90 years? Okay. And the answer is potentially this, which is nothing. It's just an empty, cold, dark universe. And the reason why is because if you look at the evolution of our universe on this nice chart here, where on the y-axis you have the scale of the universe, on the x-axis you have time, going from the beginning of the universe, what we call the Big Bang or inflation, present today, and then future here. The scale factor, this is what I was talking about before, the universe, after inflation, was getting bigger and bigger and bigger and bigger and bigger, but then gravity caused it to start decelerating, all right, getting slower and slower and slower. But then, essentially, right around today, the universe switched over from being decelerating to accelerating. And as I've already mentioned, this was due to the presence of dark energy. But since we don't know what dark energy is, there essentially are 3 possibilities of how the evolution of the universe can continue. The universe is already accelerating and getting bigger and bigger, faster and faster. So the 3 possibilities are either it continues that acceleration, getting bigger and bigger, faster and faster and faster, until eventually it rips itself apart in what we call a big rip. So it gets infinitely large in a finite amount of time. Okay, big rip, not so pleasant. Or the acceleration essentially just kind of has a steady state equilibrium of a constant dark energy in that it gets infinitely big in an infinite amount of time. Which is to say, the universe just keeps getting bigger and bigger and bigger. Galaxies are getting further and further apart. Stars within those galaxies are dying, dying, and dying. Even if they weren't dying, which they are, they would be too far away for you to even see them. All right? So this is considered essentially a cold, lonely death of the universe. If we have constant dark energy. Then the third possibility is a big crunch. That this acceleration of the universe turns over, switches back to deceleration, and then collapses back upon itself. And this is what essentially we call the Big Crunch. Okay, it's almost like an inverse of the Big Bang. Okay, so these are the 3 possibilities of how the universe will continue to evolve from today onward. And the answer of which of these ones are correct depends upon dark energy. So, what do we currently think dark energy might be? Or let me just say here, the fate of the universe is determined by the nature of the dark energy. Now, to kind of just give you the point, more or less, straight to it, we believe that the dark energy is constant. And when I say we, I don't mean me. I mean the collective group of scientists. Okay. The general consensus is that dark energy is constant. Every time we've looked at it, every time we've measured it, it appears to be constant in value. But what they don't tell you, all right, at school, is that those observations are very limited. So if you actually were to go, or I should say very local. So if you were to go even a little bit further out into the universe, our idea of the measurements of dark energy and what's called the equation of state drops significantly. Which is to say, we're still not convinced of exactly what dark energy is, but the general idea is that it's most likely a constant, which goes by the name of a cosmological constant. Maybe you've heard of this, Einstein's greatest blunder, different talk for another day. Sometimes also called lambda, all right, Greek letter lambda, okay? Now, this plot I'm showing you here is an idea of what a universe would look like with constant dark energy. So on the y-axis, you have what's called the fraction of energy density. It's just a number that goes between 0 and 1. Okay? And the universe we consider as being composed of three constituents: radiation, matter, and vacuum. Radiation domination in the early universe during the inflation of the Big Bang. Matter domination during star creation, essentially everything else. Up until today, when dark energy dominated, vacuum acceleration started. Okay? So if the universe has a constant dark energy, okay, then eventually in the future, this weird kind of axis here, this x-axis, this ln of a, don't worry about it, think of this as time. Okay? This is the natural logarithm of the scale factor, which we can use to parameterize time. Point is, this is the beginning of time here, this is today, this is the far future. If we have a constant dark energy, all right, then the universe will essentially get bigger and bigger forever. All right, and we get this cold, lonely, cold death, of the universe in the future. But if dark energy is not constant, we could get some variations. So in this particular model, known as quintessence, also known as dynamical dark energy, it says, well, hey, wait a minute, maybe dark energy is not so constant. Maybe it's modeled by a very simple potential, just kind of like we use in inflation. And thus, the energy density of the vacuum, sure, it might increase and get bigger and bigger and bigger, faster and faster, but depending on the potential, it might then turn back, oscillate, just like we saw before that inflaton, right? Like a marble in a bowl. These are those oscillations. If dark energy was something similar to inflation. Okay. So another interesting thing here is notice how the two plots I showed you, everything between the early universe and today, in terms of radiation and matter domination, is exactly the same. Look at that. Meaning, from our perspective, looking backwards in time, which is to say every time we point a telescope at the sky, or even every time you just even look at the sky, you're looking back in time, the observations would be completely identical. We would have no way of distinguishing between these two models from an observational point of view, because, as I mentioned, we have very limited observations of these parameters. So point is, the past would look the same, but the future would be very different. So in this particular case of a quintessence, dynamical dark energy dominated universe, the vacuum domination would eventually turn over, dissipate, and give rise to a second epoch of matter domination. Meaning that the universe would not die a cold, lonely death. It might actually continue living and evolving and being wonderful. Yeah?
Are you talking about the amount of the dark energy or the density of the dark energy?
So in this case, let's say density. Okay? So it's not so much the amount, but this is essentially a quintessence model. So essentially it's a potential, so essentially it's having, constituent.
So what is constant? The density is constant or the amount of the dark energy is constant?
I can actually we can actually show you right here. So check it out. So we can think of actually quintessence and constant lambda dark energy, cosmic constant dark energy. Essentially, cosmic constant could be considered a perfectly flat potential. And in fact, I might even have it right here. So, in this particular case, all right, cosmic constant would be considered having a essentially zero potential. Okay, and so this would be your potential here. So cosmic constant, essentially, you get that from quintessence. You can think of cosmic constant as just one special case of the dynamical dark energy theory.
I agree with that, but I think all the knowledge that we have, or at least that I'm aware of, is that initially potentially, because like, there is much less space, there is not enough dark energy. If the density of the dark energy is constant, then with the increased space, there is more dark energy. So I'm just trying to understand what are you trying to imply about the future. How would that change? In a very like simple conceptual way, not too much.
Oh, so you mean like just the density of
Well, there are two
quintessence?
models,
Yeah.
right? If it remains constant, I'm assuming you're saying if the density is constant or if the density is not constant. If it's
Yeah,
changing,
yeah,
that's
exactly, yeah.
somehow
Yeah.
decreasing.
I'm sorry, that's,
So what
yeah.
would cause that? For example, because the increase in the dark amount energy, if the density is constant, would be correlated with increase in space. What would cause the decrease in the dark energy?
That's a good question. Let me think about it. Maybe we can talk about it offline.
Okay.
But yeah, that's a good question. Thank you. So yeah, so just to recap here. So the general idea here is that dynamical dark energy could be modeled very similar to potential, the potential that we use in inflation. All right, such as this, same exact equations. So the equation of motion for the scalar field is the same as a particle undergoing simple harmonic motion at potential well, meaning everything we saw before from inflation could be translated over to dark energy. Yes.
So I understand, this from my perspective,
Yeah.
is dark energy relatively constant right now, from
The
our
density.
point of view, because
Yeah.
I
So
would see it, say with that model,
yeah.
it would, to me, it'd be similar to displacement.
Yeah. So yeah, this is the idea of
Same amount would still be there.
Yeah, in fact, let me just kind of talk about density. There's actually, I think, let's talk about this a little bit. When we talk about this density here, and kind of like if you had a box, right? And it's like, if you were to count like the number of hydrogen atoms in that box, essentially, that is essentially more or less constant due to this constant dark energy. Okay, when we say constant density, that's kind of what we mean there. Now, the density though, to be perfectly honest, and I wonder if I have an equation somewhere, maybe I don't show it here. Well, let me put it this way. So this W here, I didn't really plan to go into the level of DSL, but this W here is called the equation of state. And this equation of state depends upon the density. And the density in field theory can be written in terms of potential, the scalar field potential phi. So that's kind of how this kind of relates a little bit. But anyway, maybe we're going a little bit off the rails. So point is, main connection here, is that the dynamics of dark energy can be equivalent to the dynamics of inflation. It's just a difference of scale. Okay. And in fact, this is one model from recent research. All right, Kim and Al, you can look this up in the archive. Okay, this is a dark energy potential model. Okay, that looks very familiar to inflationary models. Right, and this essentially broken symmetry models can also explain dark energy. So all those observations, okay, that we've been talking about, all right, can also be explained in certain models with this potential. Now again, this is not so, it's doable, but it is a little, ad hoc. But the point is, it is possible to model dark energy with the same inflationary potentials. So far tonight, we talked about 3 examples of broken symmetry, right? Most recently, this dark energy model. Before, we talked about inflationary hilltop potential, broken symmetry, and also Kintsugi. So here, we have this wonderful situation where perhaps does nature prefer broken symmetry? Why is it that, from our perspective as humans, we consider certain things with broken symmetry beautiful, whereas nature also perhaps, I don't know, inflation, dark energy. I'll leave it to you to interpret. But here's a little interesting book, Symmetry Breaking in Biology, if you're interested in that. Little switch from astronomy. And, just kind of leave this here, let you think a little bit. But on the left, you have a neuron from your brain, okay? And over here, you have the universe on the right-hand side, the large-scale structure. And they look a bit similar, do they not? So, on that note, let me say thank you